Okay, so last time, remember, we ended the lecture by discussing some of the symmetries of the diffusion equation. And so I just want to quickly review what these symmetries are because they're going to be important for when, for the majority of the lecture, we spend, for when in the majority of the lecture, we construct solutions to the diffusion equation. And so remember the first symmetry is related to translation, meaning if I have, in all of these examples, U will be assumed to be a solution. And if I have a solution U and I translate it by, say, Y in the X direction, then that gives me a new solution, right? Where Y is just any fixed number that you want. There's also a symmetry with respect to taking derivatives, meaning if I have any solution to the diffusion equation and I differentiate it either in the x variable or the t variable any number of times, you can check that that always gives you another new solution. The next symmetry was the superposition principle, which is the consequence of the linearity of the equation, which tells you that if you take any linear combination of solutions, so here each UI is some different solution to the diffusion equation and the CI are constants, then this linear combination will give you another solution. And then we saw that there's a limiting version of the superposition principle, which tells you that, well, infinite or sums like this, if you construct them in the right way and take limits, will give you integrals. And so if you integrate any function g, where here g is just any function of one real variable, and u is a solution to the diffusion equation, then this integral will also give you a new solution. And then finally, we had this scaling symmetry, which says that if I have my solution u and I take any real number, then if I multiply x by square root of a and multiply t by a, then that gives me another new solution. And so what's you can check the scaling property just by differentiating and you'll see that it works. I mean, the idea is just, well, I have two x derivatives, right? Remember the diffusion equation is ut minus k times uxx equals 0. And so differentiating x twice will give me square root of a times square root of a because of when you do the chain rule, right? And then I have one t derivative. So differentiating with respect to t will just give me a. And this is the reason for the square root, right? Because I want these to multiply or to be equal so that I can factor out the same quantity and then multiply it by, or divide 0 by this quantity, right? And so that's the idea for how this proof of this works. And again, the motivation for the choice of square root of a for x and a for t is just, well, the number of x derivatives is twice the number of t derivatives, right? And then so this corresponds to the square root versus the power of 1. And so this may seem kind of arbitrary, like why are we interested in scaling things in this way? But this is actually going to turn out to be a very important observation for deriving the solution to the diffusion equation, which we'll see momentarily. Right. Okay, and so remember, well, what is the idea for finding a solution? Well, the idea is to use some of these observations related to the symmetries of the equation to build a general solution from a specific one. From a particular. And in particular, notice that using property D, if we can find one such solution, then if I use this integral formula, I'm going to be able to, you can obtain many more solutions, right? And so the formula that we're going to have for the solution to the diffusion equation looks a lot like, it's going to look a lot like the integral in symmetry number D, right? And so one important observation is, well, notice that from property E, which is the scaling condition, any particular solution that we find needs to satisfy the scaling property, right? It needs to obey the scaling rule. And so therefore, we're going to be able to use this scaling observation to help us determine what the initial function should be that we use to construct every other function. If we didn't have such a scaling symmetry, it would make it a lot harder to actually find a particular function that works. And so you'll see why this works soon. And so recall, well, what are we actually trying to solve? We're trying to solve the initial value problem on the real line, where x is between minus infinity and infinity. And we want a function that solves the diffusion equation with one initial condition, which is the initial state when t is equal to 0, u is equal to some function phi of x. And so that's the goal. Right, and so, right. So what did I just say a minute ago? So with symmetry, the integral symmetry, or the limiting version of the superposition principle D in mind, right? And so this is just, again, the superposition principle, but a limiting version of it. What we're going to do is we're going to guess that we can find a general solution in this integral form. Right, so we're going to guess that I can always solve the diffusion equation by writing my function u as some integral from minus infinity to infinity of some special function, which I'm going to call s of x minus y comma t, integrated against some other function g, right? Where s is a solution to the diffusion, a special solution to the diffusion equation. Right, and so the argument's going to proceed first by looking for a good candidate for S and then proving that this formula always works. So there's going to be several steps. And so this function S is typically called the source function or the fundamental solution. Because from this function S, you can build all your other solutions. Okay, and so let's analyze this further. Well, the first thing that you need to take into account is the initial condition, right? If there's no initial condition, it's a lot harder to find solution formulas, as we've seen. And so it's going to be important that my function u is equal to phi when t is equal to 0. And so you can think of this in a limiting sense, right? So the limit as t approaches 0 of u of x t, whatever the solution is, should always converge to phi of x, which is your initial condition. And so if I look at this integral below, well, what do we expect? Well, I expect that phi of x is the limit as t approaches 0 of u of x t, right? And so that means I should be able to recover my initial condition phi by taking the limit as t goes to 0 of this integral. Right, and so whatever this source function s turns out to be, I better be able to take the limit of this integral and recover my function phi. And so, well, we want s should be some specific thing. Right, this is some specific function. And so, well, if s is a specific function, how am I going to recover phi? Well, that means that g should depend on phi in some way, right? It's going to turn out that we can actually take g equal to phi, which we'll see why that is soon. But at least just from some initial observations, we can see that if we want this formula to work for s some special function, then in particular, the s should not depend on phi, because I want this to work for every initial condition. And so therefore, g has to depend on phi in some way. Right. And also, we want this limiting condition to hold, right? Where when I take the limit as t goes to 0 of this integral, I get phi again, right? Okay, and so this is the point where you need like a big idea to help you get to the next step. And so I'm just going to label this as a clever idea, just to point out that you should not be expected to just come. This is like one of those big, brilliant ideas that will change the field. The idea that led to finding a solution like this. So it may seem kind of arbitrary when I'm writing this out. It's not because I'm explaining this kind of like one step after another as if these steps come naturally. In reality, it took people, several years, possibly decades to arrive at this method. And now that we understand the method, it's not too hard to just list out in an hour, but that's at the expense of again, many years of work from like some of the best mathematicians and physicists in previous centuries, right? So this should not be easy, right? And so if you have to spend some time absorbing what's going on, that's completely normal. And so the big idea here, which is this big jump, is to, well, let's suppose that my source function s is given by the derivative with respect to x of another function q, where q is some other solution. And the idea is to pick q in a clever way so that when I integrate by parts in the above formula, I can use the integration by parts along with the fundamental theorem of calculus to help me recover my initial condition phi. Right. Well, notice that if q is a solution and I define s to be the derivative of q, then by property b over here, s will be a solution, right? So it actually suffices to find a q and then take the derivative of that, which is how the argument will end up working. And so what does this imply, right? Why is this a clever idea? Well, then we would have, well, we have /want. Let me not be like so conclusive yet. Well, we would have phi of x is the limit as t goes to 0 of integral from -infinity to infinity of the derivative with respect to x of q of x minus yt, right? Because that's what my function s is, times g of y dy. Well, I can write derivative with respect to x of this function as a derivative with respect to y of the same function, except I have to take a minus sign, right, just because of the chain rule. Right, so these are the same thing. But once I have a derivative with respect to y in the integral, I can integrate by parts, right? Right, and so I can write this integral now as limit as t goes to 0 from -infinity to infinity of, well, I'm gonna integrating by parts moves the derivative over at the expense of a minus sign. So I have a negative d dy here, and so the minus sign will cancel when I integrate by parts. And I'll have q of x minus yt, and then I'll have derivative with respect to y of g. Right, and then plus some boundary term. We're going to assume that there's sufficient decay at infinity such that this goes to 0, right? So the boundary term involves, for example, the values at infinity of the function g. In order for this formula to even make sense, we need g to decay at infinity, and therefore when you integrate by parts, the boundary terms are always going to be 0, right? So those just disappear. Well, notice, let's pretend that the q isn't here for a second, right? Let's just pretend the q isn't there. I have the integral of a derivative of g, and I want that integral to be equal to phi of x, right? So I want phi of x equals, let's forget the limit for now. Just say integral from -infinity to infinity, q of x minus y, let's say we just plug in 0 for t, times dy of g with respect to y. So notice that, let's say I can forget about the q, and let's say I can, on the support of this function q, the integral is only defined from -infinity up to the point x, right? Well, if this is the case, then by the fundamental theorem of calculus, Well, I'm integrating the derivative of g from minus infinity to x. And so the fundamental theorem tells me that this is g of x minus g at minus infinity, which we're assuming is 0. And well, I want that to be equal to phi. So if I said g equal to phi, that would work. As long as I can make this first step over here where I crossed off the infinity with the x work, right? And so what we're going to do now is just set g equal to phi, right? Which is a reasonable thing to try because it has to depend on phi in some way. So just try the easiest thing first. And what I want to do is I want to choose my q so that when I take the limit as t goes to 0, that the integral is just integral from minus infinity to x of the derivative. Right, so let me write that out. Right, so I want to choose q such that if I take the limit as t goes to infinity, no, I'm not going to write g anymore. I'm just going to write phi. I want this to equal, oh, sorry, it should be phi y. So let's just put the phi y there. I want this to equal, when t is equal to 0, integral from minus infinity to x of phi y dy. Right, because then this is equal to just phi of x. And so that's what we want for the initial condition. And so if you think about this for a few moments, you would see that, well, this means that I want q to be 1 in a certain range and then 0 and outside that range so that I kill off part of the integral. And so in particular, the following choice for q works, right? So if I let q of xt, the limit as t goes to 0, if the limit of q as t goes to 0 of q is equal to, well, let's say it's equal to 1 if x is bigger than or equal to 0, and 0 if x is less than 0. Well, what happens if I plug in, notice I have x minus y here. So then if I look at q of x minus y comma 0, this should essentially be, since I'm taking the limit, well, it should be 1 if x is bigger than or equal to y, which is exactly the range we have above, and then 0 elsewhere. Right, so that works. That would give us the formula. And so, right, I'm throwing all these formulas at you. What I would recommend doing right now is pausing the lecture on this slide and checking that if you, like double checking, don't just believe me, but double check that if I define q and if I had a function q which satisfies this condition when I take the limit as t goes to 0, that this formula above will work out. And that we'll be able to recover phi by taking the limit as t goes to 0 of this complicated integral. Right, because of course I can just sit here and tell you all these things in the video, but the best way you're going to really learn math is by actively participating, right? So you should check these things for yourself as well. And as I mentioned a few minutes ago, this should not at all be like an obvious thing to do, right? This is why I have it under the title of a clever idea, which are clever ideas are very rare in math. Usually a clever idea leads to a big development. Okay, and so now the goal is to find such a q, right? We want to find a function q that satisfies these conditions, and then I'm going to let my source function be the derivative of q, right? And so the goal is, well, I want to find a function q of xt with two conditions. Well, so the first condition is just that it's a solution to the PDE, right? So if I take d dt of q minus k times the second order x derivative of q, that this is equal to 0. And then the second condition is that if I take the limit as t goes to 0 of q of xt, that this is equal to what I have above. Right? And so assuming that both of these work, then I would set my source function s to be derivative with respect to x of q, as we saw up here, right? We saw this a minute ago. And then the final solution formula will be will be given by integrating against s. And so the solution formula will be u of xt equals integral from minus infinity to infinity of this function s, which is the derivative of q, times phi of y, where phi is the initial condition. Right, so here's your initial value, and this is your source function. Okay, and so now basically the rest of the lecture will just be spent, trying to find this function q that meets these two conditions. Okay. Okay, and so I'm gonna follow the presentation in the book pretty closely. And so what we're gonna do first is what we're gonna do is break it up into several steps so that the argument is digestible. And so the first step is to begin by just trying to find the simplest possible option, which is always a good starting point, right? You don't want to just immediately jump for a complicated guess, right? You want to try simple examples first to see if they work, right? And so what we want to do is try, well, what's the simplest option here? Maybe q is given as a function of, maybe composing a function of one variable with something that depends on x and t. So I'm going to try q is equal to g of some function p of xt, where g is a function of just one variable. Which means that the input of g is just a real number, and then I'm inputting some other function p, which may depend on x and t. But as I just said, I want this to be simple, so we're going to try to guess for a simple version of p. Right. Well, notice that, remember, we had this scaling condition, which was scaling symmetry, the last one. We would expect that no matter what p is, I should have p of, if I take p of square root of a times x, and then also at a times t, that, well, this should also be if I replace p by this value, then that should also be a solution. The simplest way for this to happen is that if p is invariant under this operation. So if plugging in square root of a times x and then a times t cancels out and I get the same value, right? So what I'm going to do is look for a function that has this property. And I'm going to end up finding the simplest function that does have this property. Well, what are examples of simple functions? Well, polynomials are probably the simplest functions to work with, which would just be combinations of powers of x and t, maybe powers of x times powers of t also. But if you think about it for a minute, you'll see that if you have a polynomial, there's no polynomial for which, in x and t, there's no polynomial for which this scaling property will hold, right? Because if I multiply the input of the polynomial by some number, well, that's going to multiply everything and they're not going to cancel out. But the next simplest thing is to just consider a ratio of polynomials. And if you take ratios of things, then when you scale the inputs, things often do cancel out. And so that motivates the following definition. Well, let me suppose p is just x on the top and then something involving t in the denominator. Well, notice if I multiply x by square root of a, then that should cancel out with multiplying t by a. And so that tells you that maybe you should take the square root of t, right, to get the square root of a's to match. And so that's what I'm going to do. So I'm going to have a square root of t. And then there's just going to be some constant c. Right. And so the good candidate for our function p is just this x divided by square root of t. And so of course, now if I plug in square root of a times x and a times t, this outputs, well, I have c times square root of ax times square root of a times t. well, the square roots of a will cancel, and so I just get cx over square root of t, which is p of xt. And so that works. Okay. And so this is a good choice for p. And so the idea or the issue now would just be to determine, well, what is the c? So c is just some constant. The way you mathematicians would have originally done this was just leave in c as it is, and then run the argument we're gonna go through in a minute, and then check that there's only one constant for which this will work. What I'm gonna do is just tell you. So it turns out that the best constant or the optimal constant or the only constant that will work is 1 over the square root of 4k, where k is the constant from the diffusion equation. Right, I mean, again, you could just check this by differentiating everything and seeing that this is what CS equal. I'm just gonna skip that step so that we can focus on the main part of the argument. And so, right, so then this leads us to the following guess. So we're gonna guess q of xt is some function g evaluated at x over square root of 4k t. And I'm often below, for this lecture, I'm gonna write this as g of p to simplify notation slightly. But remember that p is always some function of x and t. Right, the reason we write it in I'm writing g of p is to remind you that g is really a function of one variable input. We're just replacing p by something that depends on 2 variables. Okay, and so now the goal is to figure out what g has to be, right? So step 2 would be determine g. And so what we're gonna do is well, we're working with partial differential equations. I need my function q to be a solution to the PDE, which is the diffusion equation. So I'm gonna have to take derivatives and see what in order to get more information, right? So I wanna check that, I wanna determine a g so that q solves the equation, solves the diffusion equation. And so what we need to do now is take derivatives and check. Right. Okay, and so let's do that. Okay, well, let's begin by taking time derivative. So if q is of this form, what does the derivative with respect to t have to be? Well, this has to be derivative with respect to t of g composed with this other function, right? And so I need to use the chain rule in order to calculate a derivative like this. Hopefully in the first homework assignment, you got a lot of practice using the chain rule again, and now the multivariable chain rule is once again second nature. And so what is this going to equal? Well, this is derivative of g with respect to p, where I'm viewing p as its own variable, and then times derivative of p with respect to t, right? Because p is a function of t. Okay, well, what is derivative of p with respect to t? Well, p is equal to this rational function where I have t to like the -1/2, and so you can calculate using now the one variable chain rule that this is going to be -1 over 2t times x divided by square root of 4kt. And then, well, this is multiplied by the derivative of g, which is g prime, because g is a function of one variable at p, where again, p is this function x over square root of 4kt. And so again, if that step was confusing or you're not sure where I got this value, what you should do is pause the lecture and calculate this derivative for yourself, right? You don't have to have a PhD in math or anything to calculate this derivative. It's just an easy exercise in the chain rule. So if you got stuck at this step, that's fine, but pause the lecture now and just calculate the derivative and check with what I got, and you should be able to get the right answer. The right answer, excuse me. Okay, and so similarly, well, now we have the derivative with respect to t. And now what I want to do is just calculate the x derivatives. So let's do that. So similarly, if I take derivative with respect to x, well, this will be given by derivative of g with respect to p, now times derivative of p with respect to x. And this is actually easier because you don't, I mean, it's just the tx is a constant when you're differentiating with respect to x. So this just becomes 1 over square root of 4kt times g prime of p. Again, if this doesn't make sense, just pause the lecture and calculate it for yourself, and you should be able to get this formula without too much effort, hopefully. And then if I take one more derivative with respect to x, this is going to be given by, well, I have derivative of qx with respect to p times dp dx again. And so this has the effect of giving you a second order derivative of g, and then multiplying again by this thing that we got over here. So this is going to be 1 over 4kt times g prime prime of p. Right. And so therefore, if I multiply k times qxx, which is what shows up in the PDE, I get 1 over 4t times g prime prime at p. Okay, and so now remember from property 1 over here, we want q to be a solution to the diffusion equation. And so what does that mean based on these formulas? Well, we want qt minus k times qxx is equal to 0. Let's plug in. So plug in what we got above. Right, so for qt, we have minus 1 over 2t times x over square root of 4kt times g prime of p. And then for the k times qxx term, we had minus 1 over 4t times the second derivative of g with respect to p. And we want that to be equal to 0. Right, and just to clarify where we are, this is the qt term, and this is the k times minus k times qx term, right? And we want this to be equal to 0. Okay, well, what is this? Well, let's pretend that x and t are fixed. As imagine that they've been fixed and imagine they're constants. Well, this is just a second order ordinary differential equation in terms of the g's. And in particular, let me clear the coefficients of the second order derivative. So let me multiply everything by 4t, or by negative 4t. Right, so we're assuming t is not 0. Right. Let's assume t is bigger than 0. Multiply by negative 4t, what does the equation become? Right, so the equation becomes g prime prime of p, and the negatives cancel, so I get plus, well, I have 4t over 2t, so that just gives me a 2, and then I have x over square root of 4kt times g prime of p equals 0. But remember, what is p? P is x over square root of 4kt, right? And so we just see p appearing here again. And so I can finally simplify this to the following second order ordinary differential equation, which now just involves the variable p. Right? And so I get this equation. And so whatever my function g is, g has to solve this ODE. Right? And so this is it's like just a moment of just extreme luck that when you write out this, do this analysis with one of the simplest possible guesses you could make, you arrive at this ordinary differential equation, which we actually know how to solve. And so you can solve this using, if you think back to your ODE class, there are a few ways to do this. I guess the most common is the method of using an integrating factor. Remember, what are integrating factors? Well, notice that I have a second derivative and then a first derivative, right? So the first term you can view kind of as the derivative of the second term, but there's this extra piece here that's contributing, so you need to take that into account. And in particular, you can view this as like the version of like the product rule of some function, right? So view this as the derivative of, say, g prime times some other function. And so if you multiply this through by the correct choice of function, you're going to be able to take the antiderivative by reversing the product rule. And so that's what integrating factors are. And so in this case, it turns out, I mean, if you go back to your old textbook or look it up online, the integrating factor formula is always given by e to the integral of the coefficient of the term, the lower order term. In this case, it's 2p dp, which is some constant, which I'll call c1 times e to the p squared. Okay, so this is your integrating factor. Now, if I multiply this equation by the integrating factor, I get c1 times e to the p squared times g prime prime of p plus 2p c1 e to the p squared times g prime of p has to equal 0. And so you can observe that this is the derivative with respect to p of the function c1 e to the p squared times g prime of p. Right. You can check this by hand right now if you want, or just remember that this is what the integrating factor is chosen to do, right? It's chosen to allow you to write the left-hand side in this way. Right, and so this tells me that I can solve the ODE in the following way. So the differential equation has the solution, well, if the derivative of this thing in brackets is 0, that means this thing in brackets has to be constant, right? So c1 e to the p squared times g prime of p is some other constant c. Right, and so this tells me that g prime of p has to be some constant, which I'm just going to call c1 again. I'm replacing c1 by c divided by the other thing, times e to the minus p squared. And that's it. So that tells me what I haven't found g yet, but this tells me what the derivative of g has to be, where c1 is just some constant. Right. And again, if you've completely forgot about this method I just used, or you've never seen it before, it may be a good idea to pause the lecture and go review integrating factors and review how to solve ODEs, or else, like, right, this should hopefully make sense at this point. And if it doesn't, it would be worth reviewing how to solve this equation. Right, because the point of this lecture is to develop an understanding of where the solution formula comes from. Of course, we could save an hour of class time if I just omitted all of this and just gave you the formula, but then nobody would learn everything. So it's important for you to understand all these steps. And if you need to, which is perfectly fine, go back and review integrating factors so that you understand what we did in this step. Great. Okay, and so, well, now we know what the derivative of g is. And so, well, if we know what the derivative of g is, then just using the fundamental theorem of calculus, we can get a formula for g. And so finally, right, I'm gonna have to make some space. So by the fundamental theorem of calculus, well, just take the antiderivative, and that's what g has to be. So g of p is equal to some constant c1 times integral from 0 to p of e to the minus w squared dw, where w will just be my dummy variable, and then plus some other constant c2. right? So those are constants. And so at this point, I'm going to plug in, let's remember what P should be. P should be x divided by square root of 4kt. And so if I plug this in, this tells me that, well, q of x comma t, which is this function we were looking for, we said this was g evaluated at x over square root of 4kt. If I plug this in for p, I get integral from 0 to x divided by square root of 4kt of e to the minus w squared dw plus some other constant c2. And so you should recognize this as what we called the Gaussian integral from your first homework assignment. And so this calculation we did to find the value of this integral is going to be relevant for the next step, right? And so in particular, we need to determine what these constants should be, right? We don't know what C1 and C2 are, so we need to find them. I mean, in theory, remember that our source function S is going to be given by the derivative of this. So it's going to turn out that the value of C2 doesn't matter, but knowing the value of C2 will help us find out what C1 is. Right. Okay, and so now we're going to move on to step 3. Step 3 is just find the constants C1 and C2. How are we going to do this? Well, we're going to use, there's one piece of information about Q that we haven't used yet, which is the second bullet point over here, which are sort of like the initial or boundary conditions. Right, and so we're going to use these initial conditions from point 2 to find the constants. Right, so what I want to do is use the conditions from 2. Right. Okay, and so what is the first condition? Well, the first condition is a property when x is bigger than or equal to 0. And so in this case, I want limit as t goes to 0 of q of xt when x is bigger than or equal to 0 to equal 1. And so therefore, I should have 1 is the limit as t goes to 0. I'm going to replace q by this integral we found, c1 times integral from 0 to x over the square root of e to the minus w squared dw plus c2. Well, notice in this integral, the only thing that changes with t is the top bound here. And in particular, we have, well, as t goes to 0, the denominator of this gets very small, so the ratio blows up. So this goes to infinity, positive infinity as t goes to 0, right? Because, well, since x is bigger than or equal to 0, the numerator will be positive. Let's say x is not 0. Yeah, I mean, I guess you want this condition for x strictly bigger than 0. It turns out for integrals, if you change the value, I mean, if you change the bound by, if you remove 1 point from the boundary of the integral, it doesn't change the value, right? But we want this say for x positive. So let me correct that up here. Sorry about that. I mean, what I meant to say a second ago is that the integration by parts argument we looked at earlier to figure this out will not change if you do it if I change where the equality is. Right? Okay, well, anyway, returning to the main argument, assuming x is positive, then the top bound will go to infinity. And so therefore we want 1 is equal to c1 times integral from 0 to infinity of e to the minus w squared dw plus c2. But now we know what this integral is equal to because you calculated it on your first homework assignment, or maybe you've seen this before also. And so this is equal to square root of pi over 2. Right, so see homework 1. And so this tells us that, well, I need to have 1 is equal to square root of pi over 2 times C1 plus C2. Well, that's itself not enough information to actually figure out what C1 and C2 have to be. But remember, we have another condition, which we haven't used yet. So this is the second condition when x is equal to 0, or x is less than or equal to 0. Right, and so in this case, we want, well, I want the limit as t goes to 0 when x is less than or equal to 0 of q of x, t. This should be equal to 0 now. Right, remember we had this piecewise defined formula for q. And so let's just do the same thing we just saw before. So then we would need 0 is the limit as t goes to 0 of this integral of e to the minus w squared dw times c1 and then plus c2. And so while this time the numerator, or sorry, the upper bound for the integral, since the numerator is negative or 0, it's going to go to minus infinity. So let's just assume x is not 0, right? It doesn't change any of the arguments. So I'm sorry, this. Right, so this is kind of an annoying thing. So if x is equal to 0, then the integral is just equal to 0, and so there's really nothing to do. We can just, for technical reasons, we can just omit this point. But in order to explain why, I would have to use some more sophisticated results from integration theory, which everyone may not understand. So let me just believe me when I say that the x equals 0 case doesn't matter. So let's now suppose x is strictly less than 0. And in this case, well then notice that the top bound is x divided by square root of 4kt. And so now this is going to go to minus infinity, not plus infinity, but minus infinity as t goes to 0. And so from this, we conclude that 0 should be equal to c1 times integral from 0 to minus infinity of e to the minus w squared dw plus c2. And so we'll now, once again, well, this integral we have here should remind you of the Gaussian, except the only issue is that there's a minus infinity in the bound. What I'm going to do is just change variable. Right, so let's use what's a letter that hasn't showed up. Let me just use b. Let's say b is equal to minus w. We'll notice that if minus w squared is still minus w squared, right? And so in particular, minus w squared is going to be equal to minus b squared. So if I do this change of variable, the integrand isn't going to change, but it's just gonna change my bounds. And right, well, db is equal to minus dw, so there's going to be a minus sign that shows up when I do the substitution. And so this gives me, well, 0 is equal to now minus c1 times integral from 0 to infinity of e to the minus b squared db plus c2. Right, sorry, I had to erase that to clear some space, but just let me just write this out so that when you have the lecture notes later on, it's clear. But okay, and now the Gaussian integral has showed up again, except we just have a minus sign. So this is now, once again, this integral, it's the same that we saw before. So this is square root of pi over 2. And so this now tells me that 0 has to equal minus square root times pi over 2, minus square root of pi over 2 times c1 plus c2. And so now what do I have? Well, I have two different linear equations in c1 and c2. And so as everyone remembers from algebra, hopefully you can solve for c1 and c2 once you have two linear equations, right? And so this tells me that Well, I have 1, just to recap, we have 1 is square root of pi over, square root of pi divided by 2 times C1 plus C2, and 0 is negative square root of pi over 2 times C1 plus C2. And you can solve this. I'm going to omit the algebra, but if you, again, pause the lecture for a minute, we'll just add the equations, and that tells you that C2 has to equal 1/2, and then you can solve for C1. Well, C1 is equal to 1 over square root of pi, and C2 is equal to 1/2. Right. Again, just solve the system of linear equations. Okay, and so now we're almost done. So the final step is just putting everything together. Well, so what does this tell us? If we plug these into our original formula for Q, now we know what Q has to equal. And so in particular, let's plug in these constants. So Q of xt, C1 was 1 over square root of pi, times the integral from 0 to this p term. And we're integrating this Gaussian term, right? And then we just had plus C2, which is 1/2, right? Okay, and so now we have Q. We found Q, so that completes the goal. And so finally, the source function S, well, it's just given by the derivative with respect to x of Q, right? Well, notice that when I differentiate Q with respect to x, I have to use I can use the fundamental theorem of calculus to calculate the derivative, but I have to make sure I use the chain rule. And so I'm going to have to multiply by the derivative with respect to x of what's in the top bound for the integral. And so if you do this calculation, right, you end up multiplying by 1 over square root of 4kt. I'm just going to combine the square roots and write this as 4kt times pi. Maybe it's easier if I just do 4 pi times kt. And then, well, then the term that's on the top bound for the integral gets plugged into the function. So I get e to the minus, well, I'm going to be squaring it. So I have x squared divided by the denominator squared, which is 4kt. And so this is my source function, right? And so this is what's called a Gaussian, right? The reason that the integral from the homework 1 that we saw up here is called the Gaussian integral is because this function that you're integrating is called a Gaussian, named after the mathematician Gauss. Okay, and so what have we done? Well, we've proved the following theorem. Right, so suppose U is a solution to the diffusion equation. And suppose that when t is equal to 0, U is equal to this boundary function phi, meaning phi of x describes the initial state of your diffusion process. Well, then U of xt is given as the integral from minus infinity. Oh, sorry. Sorry, the pencil bugged out for a second. Right, so U is given by integral from minus infinity to infinity of the source function at x minus y comma t times phi of y dy. But now we know what our source function is. So U of xt is equal to integral from minus infinity to infinity of this Gaussian function. Well, I can notice that this 1 over square root term doesn't depend on x, so I can factor that out. Or it doesn't depend on y, sorry, in this case, right? So it's 1 over square root 4 pi kt times integral from minus infinity to infinity of e to the minus, well, I'm replacing x by x minus y squared divided by 4kt times phi of y dy. And so that's our solution formula. That wasn't very. Right. And so I mean, just to point out again, I mean, the process for finding the solution, which I'm just rewinding through very quickly on in these notes, is it was very involved, right? We needed like this really big idea even to get this argument started. And then once we had this very clever idea of trying to write S as the derivative of this special function Q, which has these limiting properties over here that I'm highlighting now, even at that point, we still have to do a lot of mathematical analysis to actually get at a formula, right? So the good news, at least though, is now that we know the formula, I mean, you can at least kind of abstractly write down what the solution to the problem is. So for example, let's suppose, say U solves the diffusion equation on the real line. Where say x is between minus infinity and infinity. And suppose that the initial state of U when t is equal to 0 is given by I don't know what's a good choice. Let's say sine of x, just to be simple, right? And so then what is the solution? The solution is given by this integral. Well, all I have to do is just plug in, this is my phi. So I just have to plug in my initial data and then I have the solution. Right, so there's no real work now that we know the formula. Right, well, what is phi? Phi is just sine of y. Right, and so that's the solution. The bad news is, well, look at this incredibly messy formula. I mean, how do I work with this function? I'm just giving you some complicated integral, which involves like a sine and then this Gaussian, which is evaluated at the input shifted by y and then divided by 4kt. And then I have this other factor that I'm multiplying by it outside. How do I actually work with this? And so unfortunately, it turns out that for most functions phi, or for most choices of initial data, it's not possible to actually evaluate this integral as a closed form function in the way that we could with the wave equation. And so what you typically would have to do is use a computer to understand the solution, right? So you would use different numerical methods to approximate the value of this integral using software. And then this would allow you to understand the solution with whatever boundary data you wanted to work with. Okay, and so that's it for today, I think. So starting next week, what we'll do is talk a little bit more about this formula and try to understand this formula and understand the source function a little more, and also compare it to the wave equation. And so that'll maybe take up about half of the first lecture next week. And then the rest of the week, we'll be looking at the non-homogeneous versions of the diffusion equation and the wave equation. It's going to turn out that the solution formulas we found here for the diffusion equation and also the solution formula, which was D'Alembert's formula for the wave equation, will both be useful for solving the non-homogeneous equation. So we've done already a lot of the hard work that needs to be done in order to solve the more general equations. Okay.